Welcome to another deep dive. Today, we're pulling back the curtain on something absolutely fundamental to the digital world. Something that quietly powers, well, pretty much everything from your quick online purchase to how complex global supply chains are managed. We're talking about data models.
Right, the hidden blueprints.
Exactly. Think of all the information swirling around, photos, customer orders, sensor readings, you name it. How is it all organized? I mean, is it like a meticulously indexed library or maybe more like a useful pile of notes?
That's a great way to put it.
A data model is essentially that blueprint, the architecture, that dictates how information is structured, stored, and crucially connected.
Yeah.
So our mission today is to really unpack the two major families. Relational, you might know those as traditional databases, and non-relational, often called NoSQL. We want to explore why understanding their differences can spark some serious aha moments about how our digital universe actually works.
And what's truly fascinating here, I think, isn't just the technical definitions. It's how these models represent fundamentally different philosophies for organizing information.
Philosophies. Interesting.
Yeah, they reflect different priorities. Maybe you need absolute consistency or perhaps incredible flexibility, or maybe it's all about the speed of understanding complex relationships. We'll try and explore these using some everyday analogies to make them feel, natural.
Okay, let's dive in then. First, big family, relational data models. When you think relational, maybe picture like an incredibly well-organized set of filing cabinets.
For interconnected spreadsheets, that works too.
Right, spreadsheets. Each piece of information has its own designated, very structured place.
That's precisely it. At their core, relational databases organize data into tables. Think of a table as a specific category, like employees or sales.
Okay.
And within each table, you have rows. Those are your individual records, like one employee or one sale. And then columns define the specific details for each record name, job title, maybe a unique ID for employees.
Gotcha. So name, title, ID in the employee table, sale amount, date in the sales table. But what makes them relational? That's the key part.
Exactly. That's where the magic happens. It's about connecting those distinct tables. So you might have that unique employee ID from the employees table appear in your sales table as well. It acts as what we call a foreign key.
A foreign key, right.
And this links a specific sale back to the employee who made it, even though the main details live in separate tables.
It's like having two separate spreadsheets, but they're perfectly synchronized because a value in one directly points to an entry in the other. Very clever.
It is. And this linking is incredibly powerful because it lets you ask complex questions.
Right.
Like, which employees made sales last month? The database can quickly join those tables using those shared keys, the IDs, to give you the answer.
And they mostly use SQL for that, right? Structured query language.
Primarily, yes. SQL is like a highly precise language specifically designed for asking questions across these linked tables. It's really good at joins and filtering.
Okay, so what's under the hood that makes this system so, well, robust?
Yeah.
You hear about relational databases being reliable.
A key aspect is that they enforce a fixed schema.
Fixed schema, meaning?
Meaning the columns of each table, their data types, everything, it's all defined up front. And every single row must conform to that exact structure. Trying to put, say, unstructured notes into a strictly defined column, it's like trying to cram an octopus into a shoebox, as you said. It just won't fit gracefully without some real effort to make it conform. But that rigidity, that's not a bug, it's very much a feature.
Right. Why is that?
This strict structure is why they're the backbone for systems where consistency and reliability are absolutely paramount. Think banks, inventory systems, HR applications.
Mission-critical stuff.
Exactly. They even guarantee something called ACID properties. Atomicity, consistency, isolation, durability.
ACID. Sounds intense.
It basically ensures transactions are processed reliably. Even if the system crashes halfway through a bank transfer, ACID ensures your money doesn't just vanish. The transaction either fully completes or it's fully rolled back.
Okay. That makes sense. Predictable and trustworthy.
Very much so.
Okay, so if relational models are these super organized, rigorous filing cabinets, what happens when your data is messier? Or it's changing super fast and those rigid drawers just can't keep up?
Well, that's precisely where non-relational models, or NoSQL, really burst onto the scene.
NoSQL.
Yeah, they fundamentally break away from those fixed tables. They offer a completely different approach, often prioritizing flexibility or scale.
And I've heard NoSQL often means not only SQL.
That's a great point. It's not always NoSQL, but rather that SQL isn't the only way, or sometimes even the primary way, to interact with the data. They emerged as the digital landscape exploded with new types of data, social media, IoT sensor data.
Stuff that doesn't fit neatly into rows and columns.
Exactly. At huge scales, the developers needed more adaptable tools. So let's maybe look at two prominent types: document databases and graph databases.
Sounds good. Let's start with document databases.
Okay. So instead of thinking about a rigid row in a table, imagine each record as more like a flexible, self-contained folder, or maybe a digital notebook.
Folder.
That's the core idea. It stores each item as a single document, often in a format like JSON, which is pretty human readable.
JSON, right. I see that everywhere.
And what's incredibly powerful here is the flexible schema,
Bing.
meaning one folder, one document can have different fields than another document, even if they're in the same collection or group.
Oh, interesting. So not every record needs the exact same structure.
Not at all. One user's document might have email and phone. Another might store a list of hobbies. A third could have extra profile details. All perfectly fine, all stored together. JSON itself is self-describing, so each document carries its own structure within it. This lets your data model evolve really fluidly as your application changes. You don't need a massive database redesign just to add a new optional field.
That sounds like a huge advantage for certain kinds of data, like semi-structured stuff.
Yeah.
Or things that change a lot.
Absolutely. Think product catalogs in an online store. A t-shirt needs size and color. A TV needs screen size and resolution, totally different attributes.
But you can store both easily in the same products collection in a document database.
Precisely. It's intuitive too, because you store the whole the product, the user profile, and all its details together in one place. Makes reading that whole object very fast.
I could see that. I remember trying to force wildly different product types into a relational model once.
Nightmare.
So many empty columns.
Document databases elegantly solve that exact problem.
Okay, very cool. Now, what about the other one you mentioned, graph databases?
Ah, yes, graph databases. Picture a network, lots of dots connected by lines.
Okay, like a mind map or a social network diagram.
Exactly like that. A graph database stores data as nodes. Those are the things, the dots and edges. Those are the relationships, the lines connecting them.
Nodes and edges. Got it.
So let's use your social network example. Each person is a node, a friendship or a follow relationship. That's an edge directly linking those two-person nodes.
Right.
And the ingenious part is that these relationships, these edges, are stored as first-class citizens. They are the structure.
What does that mean in practice?
It means instead of, say, looking up a person, then looking up their friend IDs in another table, and then looking up those friends.
Which involves potentially slow table joins in a relational database.
Right. Instead, a graph database just follows the lines, traverses the edges that are already drawn between the nodes. It makes answering questions like, who are the friends of my friends? Or, what's the shortest path between these two users? Incredibly fast.
Ah, I see. Because the connections are literally stored as connections.
Exactly. It's optimized for traversing relationships. Things that would be computationally really heavy for other database types become natural and quick in a graph model.
So this must be amazing for anything where connections are key.
Unparalleled. Social graphs, obviously, but also fraud detection, looking for rings of suspicious accounts or transactions linked together. Recommendation engines, people who like this also liked that, which is all about connections.
LinkedIn's people you may know must be using something like this.
Almost certainly. That ability to quickly navigate complex networks of connections is a classic graph database use case. And you can easily add new types of nodes or relationships later without breaking everything.
Really powerful stuff. Okay, so we have relational, document, graph. Quite the toolkit.
Indeed. And with these powerful options, the big question always becomes, how do you choose the right tool for the job?
Yeah, how do you strategically deploy them? Because each one seems to excel in different areas.
That's the key, understanding the nuances and matching the model to your data and what you need to do with that data.
Okay, so let's try and summarize. When should you reach for each one? If you're facing a data challenge, how do you pick? Let's start with relational.
Right. Relational databases, your tables and rows, these are your champions when data integrity, transactional consistency, that ACD stuff, and a predictable structure are absolutely non-negotiable.
So financial platforms, accounting systems, anything highly regulated where every piece of data must fit perfectly.
Exactly. If you think of your data naturally fitting into neat, interconnected spreadsheets or tables, relational is almost always your go-to.
Makes sense. Okay, what about document databases, those flexible folders?
Document models are perfect when your data is semi-structured, maybe highly varied, or you know it's going to evolve a lot over time.
Like that product catalog example. Or maybe user profiles where you keep adding new preference options.
Perfect examples: content management systems, user profiles, catalogs. Anywhere, each record might be a bit unique, or you need to store complex objects that might change shape. Their flexibility is a huge win there.
And they're often intuitive because the whole thing is stored together.
Right, which makes fetching a complete record very efficient.
Okay, lastly, graph databases. The networks.
Choose graph when the relationships between your data points are the absolute core of the problem. Not just the data points themselves, but how they connect.
So finding hidden connections, complex patterns.
Yeah, performing those rapid multi-hop traversals, who knows whom, fraud rings, network mapping, sophisticated recommendation engines. If you need to navigate lots of links very quickly, graph databases are built for that specific kind of speed. They'll significantly outperform others on those tasks.
So it really depends on the shape of your data and the questions you need to ask most often.
Precisely. Each model offers a different lens. Relational, the master organizer for precision. Document, the adaptable shapeshifter for varied records. Graph, the ultimate map maker for navigating connections.
And it's probably worth mentioning lots of big modern applications actually use multiple types, right?
Oh, absolutely. It's very common now to see polyglot persistence using different data models for different parts of an application, leveraging the strengths of each. Maybe relational for user accounts and billing, document for product catalogs, and graph for the social features.
Mixing and matching for the best result.
Exactly.
So whether your data needs that unwavering precision of a filing cabinet, the freedom of flexible notebooks, or that intricate map of connections, there's a data model designed for it. Understanding these blueprints really helps you appreciate the hidden architecture under the hood of the digital world.
Definitely. And by consciously matching your data's nature and your query patterns to the right model, you set yourself up for success, keeping data organized, accessible, and your systems running smoothly.
We really hope this deep dive into data models gave you some new perspectives. Now, maybe think about the apps you use every single day. Social media, banking, streaming.
Yeah, try to guess.
Try and guess which data model might be powering their core features. Relational, document, graph, maybe a mix. It might just surprise you how much these underlying structures shape your digital experience.
It's a fun exercise.
It is. That's all for this deep dive. We'll catch you next time for more fascinating insights.